Hey guys, today we're going to talk about chapter 17, second order differential equation. This presentation is presented to you by the 830 team and the 1230 team. Second order differential equation involve the unknown function y, is derivative the first and the second, and a variable x. It comes in two flavors, a homogeneous linear equation and a non-homogeneous linear equation. This form right here, this is a second order differential equation. A homogeneous linear equation can apply to analyze a free vibration of an object. Free vibration is when an object vibrates within itself and there's no external force pushing on it. Like a tuning fork, when you hit it, the metal will vibrate, but there will be no external force shaking it. The second is a damped mass system spring system. This is a hydraulic system within the suspension system in your car that help absorb all the shocks from the road, so you have a comfortable, smooth ride in your car. So we can start with the general equation of a second order differential equation, and we set it to equal to 0. This means this is a homogeneous linear equation. We can rewritten as a y double prime, y prime, and a y. We assume that y1 of x and y2 of x are solutions of this equation, and c1 and c2 are the constants. We have a linear combination equation, a y double prime plus b y prime plus cy is equal to 0. Now we substitute y with a lambda in the linear equation. We get an auxiliary equation, or also known as a characteristic equation of a second order homogeneous linear equation, which is a lambda square plus b lambda plus c is equal to 0. We change, we substitute y with lambda and change it to a polynomial equation, is so that we can solve the equation much easier than dealing with a bunch of derivative. And we can find lambda by using either factoring or a quadratic formula method. This homogeneous linear equation has three forms, or three cases. The first case is where b squared minus 4ac is greater than 0, which means lambda 1 and lambda 2's are both real solution of the auxiliary equation. So we have a solution of y equal to c1e to the power of lambda 1x plus c2e to the power of lambda 2x. We have these two different lambda is because they are both solution of the equation and they are linearly independent, meaning y1 and y2 are not multiple of each other. And in case 2, we have b minus 4ac is equal to 0, which means there will be only one solution of lambda from the auxiliary equation y. So the solution, we would have a y equal to c1e lambda x plus c2e to the power of lambda x. And notice that these lambda are the same, so they are not lambda 1 and lambda 2 anymore. and we will have a general solution, or a more general solution is y equal to c2e to the power of lambda x, because the other term, the c1e to the power of lambda x, is just gonna go to 0. In case 3, where b squared minus 4ac is less than 0, the roots of the auxiliary equations are complex number, where lambda 1 equal to alpha plus I beta, and lambda 2 equal to alpha minus I beta. And instead of dealing with the imaginary number I, we can put it in form of cosine and sine. So we will have y is equal to e to the power of alpha x times c1 cosine beta x plus c2 sine beta x. And in order to find c1 and c2, we rely on the initial value and a boundary value condition, which means the problem would give you either a initial value or a boundary value to the along with the equation that's given. So in this case, we will look at the initial value conditions. We were given with an equation, as you can see, the lambda 1 and lambda 2, which means this is a case 1 where b squared minus 4ac is greater than 0. So we have two different solutions for lambda. And we will divide the equation. We get lambda 1 c1 e to the power of lambda 1x plus lambda 2 c2 e to the power of lambda 2x. And when we can plug in the initial value, we get y0 is equal to c1 plus c2, and the y prime 0 will be equal to lambda 1 times c1 plus lambda 2 times c2. We can just get rid of this term where e to the power of lambda 1 and lambda x. Lambda 1 and, I'm sorry, lambda 1x and e to the power of lambda 2x. Now we solve for c1 and c2 with the known lambda and the initial conditions. Now this is the case where we look at the boundary value conditions where it was given in the problem. Now we have this case, it's the same case, case 1. And we have the boundary conditions here, where is ya and yb. And we set it equal to the equation. And we can use the system, we can solve it with a system of equations to get c1 and c2. Here's an example of an initial value problem. We were given with a function with an equation y double prime plus y prime minus 6y is equal to 0, and initial values of y0 is equal to 1 and y prime 0 is equal to 0. Now we substitute in lambda, we will have this polynomial equation. Now we solve the polynomial equation and we get lambda is equal to -3 and lambda is equal to 2. Now we plug that into a solution of case 1 since we have two different lambda. So we have c1 e to the power of -3x plus c2 e to the power of 2x. And then we derive this equation. We get y prime x equal to -3 c1 e to the power of -3x plus 2c2 e to the power of 2x. Now we can use these two equations and the initial values to solve for C1 and C2. We can set y0 is equal to C1 plus C2, which is equal to 1, and y prime 0 is equal to negative 3C1 plus 2C2 is equal to 0. And we can solve it with a system of equation. And we have y equal to 2/5 e to the power of negative 3x plus 3/5 e to the power of 2x. Now let's look at a boundary value problem. So we're given with an equation and a boundary conditions where a initial value of x is equal to 1 and a final value is 3. We substitute in lambda for y as same as the other one, and we solve for lambda. In this case, lambda only one solution, which means this is a case 2. So we have this equation here where y of x is equal to c1 e to the power of negative x plus c2 e to the power of negative 1 x, negative x. Notice that the lambdas are the same. So we get, with the boundary, we get y0 equal to c1 equal to 1, and y1 equal to c1 e to the power of negative x plus c2 e to the power of negative x equal to 3. By solving the system of equation, we get c1 equal to 1 and c2 equal to 3e minus 1. Then we put all these solution into a general solution where we will have y equal to e to the power of negative x plus 3e minus 1 times x times e to the power of negative x.
Non-homogeneous linear equation. In this section, we'll learn how to solve second-order non-homogeneous linear differential equations with constant coefficients. Now, this could be applied to force vibration analysis of resonant vibration and electrical current, which we'll learn in further sections. Now, a non-homogeneous linear equation is of this equation where p of x, q of x, and r of x are constant, and that equation is equal to g of x, where g of x is a continuous function that is not equal to 0. Now, there's going to be two methods to solving these non-homogeneous equations. The first method is the method of undetermined coefficients. The second one is the method of variation of parameters. Now, the first method is the method of undetermined coefficients. Now, to do this, you find the general equation, and to find the general equation, you get it by adding the complementary equation and the particular equation. Now, the complementary equation is the solution solved by the homogeneous equation, and the particular equation is the one solved by the non-homogeneous linear equation. Now, to find the complementary equation, yc of x, you find the homogeneous solutions, and you find the eigenvalues, and you plug it back into yc of x, and you get that part of the solution. Now, to get the particular equation, yp of x, you have to guess the function to represent g of x. Now, a good way to do this is, for example, if g of x is equal to e to the power of kx times p of x, where p is a polynomial of degree n, then try yp of x is equal to e to the power of kx q of x, where q is the nth degree polynomial. Now, if g of x is equal to e to the power of kx times p of x cosine mx, or if cosine was replaced with sine, then you would use that g of x is equal to e to the power of kx, blah, 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 cosine mx, and then plus e to kx sine mx, that equation right there. Now, it is important to note that if one of the particular solutions is the same thing as the complementary equations, you have to make sure to multiply by x or x squared, where x or x squared is a vector, so that this is the solution. The solutions aren't linearly dependent; that they're linearly to make sure that they're linearly independent. That way, we can span the whole space. Now, the second method is by the method of variation of parameters. Now, suppose we already solved the homogeneous equation, and we write the solution as y of x is equal to c1 y1 of x plus c2 y2 of x, where y1 and y2 are linearly independent solutions. Now, let's replace the constants or the parameters c1 and c2 in the equation by arbitrary functions u1 of x and u2 of x. We look for a particular solution of the non-homogeneous equation of the form yp of x, u1 of x, y1, blah, blah, blah. This method is called variation of parameters because we have varied the parameters c1 and c2 to make them functions. Now, we take the derivative of the yp, and then since u1 and u2 are arbitrary functions, we can impose two conditions on them. One condition is that y of p is a solution of the differential equation. We can choose the other condition so as to simplify our calculation. So it's going to be u prime 1 y1 plus u2 prime y2, is we're going to set that equal to 0. So first we take that yp of x function, then we take the second derivative, then we find the y prime, y double prime, and then we plug that into auxiliary equation, and then we simplify, and then we solve for u1 prime, u2 prime, system of equations, and then we plug in u1 prime, u2 prime to get the general equation. Now, just as an example, we have y double prime plus y is equal to tan x from 0 to pi over 2. So first we get the auxiliary equation, and then we take the derivative, and then we set y prime 1 sine x plus y2 cosine of x equal to 0 to simplify further. We plug that in, we solve for u, we get u1 prime is equal to sine x, u1 is then equal to negative cosine of x. Then after we plug everything in, we find the solution is y of x is equal to that equation right there.
This is section 17.3, applications of second order differential equation. For a vibrating spring, we can get a formula by integrating Newton's second law into Hooke's law. We get this formula, and we can convert it into a auxiliary equation. We have m lambda squared plus k equal to 0. Then we solve for lambda, and lambda has a complex number, the imaginary number, which is the case 3. We can replace it with cosine and sine, where we have x of t equal to c1 cosine omega t plus c2 sine omega t. Then it can be rewritten as x of t equal to a cosine of omega t plus delta, and this is in the equation known as a simple harmonic motion.
A spring with a mass of 0.2 kilograms has a natural length of 0.5 meters. A force of 25.6 newtons is required to maintain it, stretched to a length of 0.7 meters. If the spring attached to a length of 0.7 meters and then released with an initial velocity of 0, find the position of the mass at time t. So using Hooke's law, we are able to input the equation k times 0.7 minus 0.5 is equal to 25.6 newtons. So we solve for k, and we find that k is equal to 128. Then we take the second order equation, which is 2 times second differentiation of dx over dt squared plus 128x is equal to 0. Then we substitute 2 lambda to the second plus 128 is equal to 0. Lambda is equal to 8. Then we get x of t is equal to c1 cosine 8t plus c2 sine 8t. Then x prime of t is equal to negative 8 c1 cosine 8t plus 8 c1 sine 8t. And then x of t is equal to 1 over 5 cosine 8t. Damped vibrations. Newton's second law with damping constants. M second derivative x over dt to second derivative plus c dx over dt plus kx is equal to 0. We have the auxiliary equation m lambda squared plus c lambda plus k is equal to 0. In order to find lambda, we use the equation lambda is equal to negative c plus or minus the square root of c squared minus 4mk all over 2m.
Damping vibration has three cases. Case number 1, where c squared minus 4mk is greater than 1. This is also known as overdamping, where lambda 1 and lambda 2 are distinct roots of each other. So we will get a solution of x equal to c1e to the power of lambda 1t plus c2e lambda 2t. In case 2, where C2 minus 4mk is equal to 0, this is the critical damping, where lambda 1 and lambda 2 are equal to each other. So there's only one solution for lambda. So we get a solution form of x equal to C1 plus C2 times e to the power of negative c over 2m times t. And case 3 is where C2 minus 4mk is less than 0. This is underdamping, where lambda 1 and lambda 2 are complex number, where we have omega is equal to square root of m 4mk minus C2 over 2m. And the solution we will get, instead of using the imaginary number, we will have x equal to e to the power of negative c over 2m times t times c1 cosine omega t plus t2 sine omega t.
Suppose previous example, immersed in fluid with a dampening constant c is equal to 40. Find the position of the mass at the time t. If it starts from the equilibrium position and it is given a push to start of the initial velocity of 0.6 meters per second. So we use the second order equation 2 d2x over dt squared plus 40 dx over dt plus 128x is equal to 0. Then we substitute in lambda, 2 lambda double prime plus 40 lambda plus 128 is equal to 0. So we simplify, and lambda double prime plus 20 lambda plus 64 is equal to 0. We solve for lambda, finding lambda 1 is equal to negative 4, and lambda 2 is equal to negative 16. Then we get that x of t is equal to c1 e to the negative 4t plus c2 e to the negative 16t. Then we derive that x prime of t is equal to negative 4 c1 e to the negative 4t minus 16 c2 e to the negative 16t. X prime to the 0 is equal to negative 4c1 minus 16c2 is equal to 0.6. X is equal to 0.5 e to the negative 4t minus e to the negative 16t. Forced vibrations. Besides the restoring force and the dampening force, the motion of the spring is affected by the external force, F of t. M d squared x over dt squared plus c dx over dt plus kx is equal to ft. A common external force is a periodic force function. F of t is equal to f naught cosine omega naught t, no dampening force. X of t is equal to c1 cosine omega t plus c2 sine omega t plus f naught over m omega squared minus omega naught squared times cosine omega naught t. If omega naught is equal to omega, there is resonance. Electric circuits. The sum of voltage drops across the resistor, inductor, and capacitor is equal to the electric motive force. Using the second order linear equation, L d squared O over dt squared plus R dO over dt plus 1 over CQ is equal to e to the t. So then you substitute lambda in L lambda squared plus R lambda plus 1 over C is equal to e to the t. Then we solve for lambda, and lambda is a positive or negative constant. Using the complementary equation, qc to the t, or finding a particular equation, qp to the t. Find the charge and the current time at time t in the circuit if R is equal to 40 omega, L is equal to 1H, C is equal to 16x 10 to the negative 4F, e to the t is equal to 100 cosine 10t, when initial charge and current are both 0. So we get the second order equation, d to the second o over dt squared plus 40 do over dt, 625q is equal to 100 cosine 10t. Then we substitute in lambda squared plus 40 lambda plus 625 is equal to 0. We solve for lambda, and lambda is equal to negative 40 plus or minus the square root of negative 900 over all over 2, which is equal to negative 20 plus or minus 15i. Then we use the complementary equation, and qc of t is equal to e to the negative 20t times c1 cosine 15t plus c2 sine 15t. The particular equation is q particular t is equal to a cosine 10t plus b sine 10t. Then we solve for a and b, and a is equal to 84 over 697, and b is equal to 64 over 697. And then the general equation is qt is equal to e to the negative 20t times c1 cosine 15t plus c2 sine 15t plus 84 over 697 cosine 10t plus 64 over 697 sine 10t.
17.4 Differential equation as series. Linear differential equation as power series. First, we assume y equal to f at x equal to the sum of cn times x to the n power. And this we can expand out into initial c plus c1x plus c2x squared plus c3x cubed and so on exists. Determine the coefficients. Then we differentiate it. We get this series here, which end up into a sum of n plus 1 times c n plus 1 x to the n, and we derive it again, you get a second order differential equations here, and we put both of them together, we have this here, the sum of 2n to the factorial c and 2n x to the power of n. Then we substitute each sum of f of n, f of x to the n derivative in differential equation and factor out x to the power of n. Now we recognize our coefficients of x of n is equal to 0. This gives us a recursive equation. Let n equal to 0, 1, 2, 3, 4 integers. Relate C4 to C2 to C0 and C5 to C3 to C1. Notice the pattern from n equal to 0 to n equal to 4 or further. Recursive equations, even coefficients c to n 2n related to c0. The odd coefficients c2n plus 1 related to c1. Substitute our coefficient values c0 and c1 into y. We factor out c0 and c1 from each series and convert each Maclaurin series to its respective familiar functions. For general solution, we get y equal to c0 times y1 plus c1 times y2. If any series is not a Maclaurin after factoring out c0 and c1, which is usually the case, then we can leave each function in its summation form. This is not uncommon. For instance, this shows up in quantum mechanics and Schrödinger equation. If we don't have a Maclaurin's series after factoring, then leave the series as they are. Lots of physical application require us to leave differential equation as power series solution. Example 1. We'll solve y double prime plus y equal to 0, a simpler equation. To clearly illustrate this power theory applies. We assume that y equal to the sum of Cn times x to nth power exists. After differentiating twice, we have y double prime equal to a sum from 2 to infinity of n times n minus 1 times c n times x to the power of n minus 2. Before adding y double prime and y, we want to keep the infinite sum starting points consistent. We get y double prime equal to a summation of n plus 2 times n plus 1 times c n plus 2 x to the nth power. We substitute each sum. We get y double prime plus y equal to 0 equal to all of this from y double prime and all of the summation from y, and we have an equal to 0. Now, n domain is from 0 to positive infinity. For each sum, 0 equal to the summations of n plus 2 times n plus 1 times c n plus 2 plus cn times x to the power of n. But x to the power of n is not equal to 0, so n plus 2 times n plus 1 times c n plus 2 plus cn is equal to 0. Recursive relations tells us that c n plus 2 equal to negative cn over n plus 2 times n plus 1, where n are integers from 0, 1, 2, 3, and so on. Now n equal to 0, c2 equal to negative c0 over 2. When n equal to 1, c3 equal to c1 over 6. And when n equal to 2, c4 equal to negative c2 over 12. c4 relate to c0, so negative 3 times 4 times c4 equal to negative c0 over 1 times 2, where c4 equal to c0 over 1 times 2 times 3 times 4, which is equal to c0 over the factorial of 4. N equals 3, where c5 equal to negative c3 over 4 times 5 equal to c1 over 2 times 3 times 4 times 5 equal to c1 over 5 factorial. And it's similar for n equal 4. We get c6 equal to c0 over 6 factorial, and also n equal to 5, we get c1 over, or negative c1 over 7 factorial. Notice the recurrence for even coefficient c2n equal to negative 1 to the power of n times c0 over 2n factorial. For odd coefficient, we get negative 1 to the nth power times c1 over 2 plus n, 2 times n plus 1 factorial. Now we substitute our coefficient value c0 and c1 into y, then factor expansion. We get y equal to c0 plus c1x plus c2x squared plus c3x cubed plus c4x4 plus c5x fifth plus and so on into the series. And we can put that in terms of the factorial, like we already went over here. We will see c0 plus c1x plus minus c0 over 2 factorial times x squared minus c1 over 3 factorial times 3x cubed, and so on into the series. And we can simplify that, or we can factor out the c0, and we have all these terms left inside the parentheses. We can factor out c0 and c1. So now we rewrite the series as sums. We get y equal to c0 times the summations of negative 1 to nth power from 0 to positive infinity plus c1 times negative 1 to nth power times x to the power of 2x, or 2n plus 1 over 2n plus 1 factorial from 0 to positive infinity. Now we have identified the recurrent series, and we found the familiar function solution, which is y equal to c0 cosine x plus c1 sine x. Here's another example for differential equation as a series. Now let's solve y double prime minus 2xy prime plus y equal to 0. We assume y equal to a summation of cn x to the power of n exists. Then we have 2xy prime equal to 2x times summations of ncn times x to the power of n minus 1, and y double prime is equal to the sum of n plus 2 times n plus 1 times c n plus 2 times x to the power of n also exists. Now we substitute each sum into y prime and 2xy, y double prime minus 2xy prime plus y equal to 0. We got all these terms here, all these summations, and it's equal to 0. Now we simplified it, we get a summations of n plus 2 times n plus 1 times c n plus 2 minus 2n minus 1 times c n, and all of it multiply with x to the nth power equal to 0. Now the coefficients is equal to 0 yield a recursion relation where n plus 2 times n plus 1 c n plus 2 minus 2m minus 1 times c n equal to 0. Now we find c n plus 2 is equal to 2n minus 1 times cn over 1 plus n plus 1 times n plus 2 for n equal to integers of 0, 1, 2, 3, 4, so on. When n equal to 0, c2 is equal to 0, negative c0 over 2 factorial. When n equal to 1, we get c3 equal to c1 over 3 factorial, and also the same for n equal 2, n equal 3, 4, 5, 6, 7. Now we discover the pattern. We have a even coefficients of c2n equal to negative of 3 times 7 times 11 to times 4n minus 5 times c0 over 2n factorial. And the odds coefficient is of c2n plus 1 is equal to negative 1 times 5 times 9, and so on until 4n minus 3 times c1 over 2n plus 1 factorial. Now we substitute our coefficient into y, then we factor it. Now we substitute, we will get y equal to c0 plus c1x. This is the general form, and then we substitute it in. Then we factor out c0 and c1. Now we cannot express y1 equal to 1 minus x squared over 2 factorial minus the sum of 4n minus 5 times x to the power of 2nth over 2nth factorial, nor y2 equal to x plus a sum of 4n plus 3x to the power of 2n plus 1 over 2n plus 1 factorial in terms of familiar functions, because neither are Maclaurin series. So we keep our solution in a summation form as here. We got y equal to y equal to c0 times 1 minus x squared over 2 factorial minus sum plus c1 times x plus this summation here. Thank you for watching.